Hello and welcome back. Today we are going to talk about support vector machines and we are going to see how R can handle support vector machines. In order to use support vector machines in R, we need to install a new package, and the package we need to install is called E1071. That's a very weird name. The name came from the room in um, Berlin University where um, where this package was being introduced. So you need to install this package first. It's E1071. I think it's still working on it. Install packages E1071. Yeah, it shows that it's been downloaded and uploaded. And by the way, in today's lecture, I'm going through the lecture notes step by step. Instead of typing things, I'm just going over the commands here because I think it's a long lecture. If I want to type it, it would take a long time. So let's go over the lines step by step. So the first thing I want to do is just create a random sample by which I can test support vector machines on. So the first step is to create some random variables. I'm interested to first introduce 40 40 observations from standard normal distribution. The standard normal distribution has mean 0 and standard deviation 1. And I want to put it in two columns. So I want to produce 40 random numbers from normal distribution, putting in two columns. So we will have two columns. Each column will have two observations. Each column will have 20 observations. So let's look at the outcome of X. So let's look over X. So X will look like this. It has two variables. So each row will have two variables because we had 40 observations in total. We put it into two columns. So each column will have 20 observations. So these are my X's and X1s and X2s. So for first observation, my X1 is negative 0.62, second observation 0.9, and so on and so forth. So these are just randomly generated numbers. And let's also generate random y's. So I just generate random y's. Let's look at different outcomes of y. So the first 10 elements of y will be negative 1. The second 10 elements of y will become 1. See that? The first 10 elements are negative 1. The second 10 elements are 1. Now I want to make sure, now I want to make some changes to that. And what I want to do is to change the values of y that are 1, which are value 11 to 20. I want to add one value to these observations from 11 to 20 based on that. So I don't want to change the first 10 observations of X. I only want to change the second 10 observations of X because these are the only ones that have Y1. Okay, so the way you do it is pretty simple. In R, you just write Y, X of Y's when are 1 will be replaced by X of Y is equal to 1 plus 1. That means for the places that Y was 1, which are 11th place to 20th place, we add one value to X and add it to X. So let's see the outcome. So just focus on, let's say, 20th observation was 0.5 and 0.7, as you can see here. Now after this change, let's look at the 20th observation. It became 1.59 and 1.6. So it added one value to both of them. We do it to separate these 10 observations from the earlier 10 observations. Okay, so let's plot what we have. Let's plot X based on different colors. So let me explain what this does. It says plot X by the colors of Y. So when Y was negative 1, it will use color 4, which is red. When Y has value 1, which is 10th to 20th observation, it uses color 2, which is blue. So let's plot that. So the random numbers we created now would look like this. we have 10 blue observations, 10 red ones, and as you can see, since we added 1 to the cases where y was equal to 1, we see the clear distinction of x1 and x2, and it's not hard to see. It's a line that separates this. This is an error we see, that's fine, but what we want is to find a line and support vectors to separate this space into two categories. So let's put all x's and y's in a data frame and call it that. That will be our data now. So that has the first two elements will be the first two elements of x, and the last part is a categorical value of y. So let's look at that. So that are the first two elements came from x. The third element is the category that it belongs to. Okay. So in order to use support vector machines, we need to use library E1071. So we are done with just simulating our data, creating a data set that has -1 and 1 category. Now we want to use our support vector machine to solve it. If you just want to use a simple support vector machine that's just linear, you have to use function svm. You first show what is your categories. What are your categories? We have two categories, and they are in my y variable. They are in my y variable here, right? So these are my y variables. So these are my categories. They're outputs. Then you regress it on x1 and x2. If you just wanted to refer to them and x1 and x2, you should write that $x1, that $x2. But here, since we want to regress it in both parts, we just put dot. That means both x1 and x2. The data we are going to use is that. So data is equal to that. The kernel type we are going to use is linear, because that's what we want. Later on, I show you how to use radial and polynomials. So let's stick with linear one. And linear, you have to define the cost that you let it have. So, and always set scale to false, so that it understands you need to scale it or not. So since we just use standardized data, we didn't need this scale. So SVM fit is a support vector machine model on y variable, which was our output, and my inputs. So let's look at the plots. One of the great things about this library is that when you plot your support vector machine fit, your model on your data, it shows the support vector it shows us. It doesn't look quite linear in this case, but believe me, it's line as just the way the plot works here. It just it looked at different meshes and just connect the meshes, and it's no surprise that it doesn't look quite linear, but that's line. It tried its best to show a line to you. And these x's here are support are elements of my support vector. So as you can see in this graph, so anything before this is blue, anything after this is categorized as red, and as we can see, there is one observation right here. This observation is misclassified. Everything else is pretty much classified, and our support vectors would be a line parallel to our boundary here, and another line which is right here. Okay, so that's how we just plot the support vectors. Let's look at the elements of the SVM feed. So the elements of our support vector can be retrieved by just writing your model $index. So it says my first observation, second observation, fifth observation, seventh observation, 14th, 16th, and 17th observation are in our support vectors. So my first observation was -0.6 and 9.91. Second observation was also clear, and so on and so forth. So you can get the elements of support vector by just writing SVM feed, which was our model, $index. It will give me the indices of the observations that became support vector. You can also look at the summary of that. There is not that much you can get from summary. The only things that are interesting is that it has 7 support vectors. So we in the support vector index, we found there are 7 observations that vary in support vector. So you can have this number here. It says 4 of the first category, 4 of my first category class, 4 of the observations of my first category vary in support vector, and 3 from my second category. And we saw it here. 4 of the first category was here, 3 of the second category. It says we have 2 classes, and our classes are indexed by a -1 and 1. So one thing we can do is to change the parameter that we can play with, and that is cost. So before we used cost 10, now let's change cost to 0.1 and see how does that work. If we change our cost to cost 1, you see our boundary will change, and way more observation will be in our support vector in comparison to before. Before we only had 7 observations in our support vector. Now we have way more. So let's look at the summary of new fit. You can see, oh, that is SVM fit. Okay. Yeah, as you can see, there's 16 observations now in support vector, which is significantly more than this. So by playing with cost, will be more and more observation in your support vector. But what is the best cost to use? In order to use the best cost, we have to use cross-validation. So the way you deal with cross-validation is pretty simple in support vector machine, and the function you use is called tune. Tune is a function that is used for cross-validation of support vector machines. You first need to set your seed to a random number that you're interested in. So tune is a function. The first thing you need to do is to introduce which model you're interested to tune your functions upon. So here we're using SVM because we are in the realm of support vector machines. So our model type is support vector machine. Within the support vector machine, we have y variables, which are outcomes, which will regress on everything else. The data we're using is that data, the one that we just created, the simulated data that we created. The kernel we are going to use is linear, and one thing wonderful about it is you just need to show what variable you want to change for cross-validation. You can have more than one or just one variable. So you have to put it in ranges. So the ranges would be the variables needed to be changed, and the variable that we change can be a list of many things. Here the list is only cost. The cost will be changed from 0.001, 0.01, 0.1, 1, 5, 10, 200. So these are the values of cost we want to change. And all of them are cost. So that's why we said, okay, the ranges that we want to change is upon cost. And this cost can get these values. So the tune will take care of that. And I think the default is 10-fold cross-validation. So let's look at the summary of these tuned parameters. So in tune out, when you take the summary of this tune out, what you get is first what method was used. This is 10-fold cross-validation. We were right about that. It says what was the best parameter that gave me the best performance, and it said for cost 0.1 among all the costs we put here, it did the best model. So our best model were related to cost 0.1. It's extremely easy. You don't even need to look at the plots to get it. It automatically gives you this value. So cost 0.1 became our best model, and it's very easy to get the best model from this tune out function. The only thing you need to do is write tune out, which was the name of which was the variable we put our tune function in, $ best model. It puts the best model inside best model. So when you get a summary of best model, it says, okay, the best model is the linear model that has cost 0.1. It has 16 support vectors, and I think what you see here is that best model, and so on and so forth. So it's very easy to extract the information on best model just to write $ best model to get the attributes of the best model and call it best model. Now let's focus on predicting. So far we've learned a couple of things. So let's review the things we've learned so far. So far we learned how to create some random numbers. I think you knew how to do it before, deal with that before. We learned how to work with linear support vectors, with kernels that are linear. We learned how to find the best model, how to tune cost. So we use tune function, and we learned how to get into the best model of all our cross-validated models. So now let's focus on something new, and let's focus on prediction. So instead of just using our training data to predict what is happening on our test, let's just create some new data, and let's call them test data. So our test data is again created based on a standard normal distribution with 40 observations. We put it in 2 columns, so we have 20 observations in total. So my x test. So if we want to just see what x test would look like, just write x test. So there are 20 observations. I have x1 and x2s. Let's also introduce y test, which is our outcome, and let's do a random thing. Here, let's sample from -1 and 1, 20 of them, and let replacement happen. If you do not write replacement equal to true, what will happen is that it can only choose 2 of these values, -1 and 1. After that, it will be exhausted because there are not 20 observations between -1 and 1. There are only 2 outcomes. So we let replacement happens. So let's look at the value of y test now. So y test can only get values of 1, -1. Since we let replacement happens, you can see that there are many -1s and many 1s. So as before, let's add 1 value to the cases that test y test is equal to 1. So for my first category, I add 1 values to x1 and x2. And let's create test data frame as my x test, the ones that we created and we manipulated, and new y's. So our test data is now composed of x1s and x2s and their categories. So we know that our test data has this, so my first one has actual outcome of 1. We know the second observation has actual of -1, but let's see how my best model works on these predictions. So in order to use prediction, you use predict model. And remember, we defined best model was the model that came from a cross-validated model on best dot model. So that is my best model. So I want to predict my test data on my best model. So this is the model I want to use, and this is the data I'm going to use. So y prediction has the predictions that you are interested in. So let's look at y prediction. It says, for example, it predicts my first observation belongs to 1. See, my first observation was actually belonged to 1, so that was the correct prediction. The 3 next observation belong to -1. As you can see, the second and third observation actually belong to -1, but this one was misclassified, and so on and so forth. So now we want to see that in the table. We want to see what is the table, the confusion matrix of actual predictions in comparison, actual observations in comparison to our predictions. So the table we are going to use has y prediction as predictions and uses y variable of our test data for truth. So one thing to remember here is the way you just refer to prediction is by calling predict, and the way you refer to truth or actual things is by using truth in the table. Okay, so y prediction was my predictions, that's why I put it in the predictions in the table, and truth was test data of y. So let's look at the confusion matrix here. So as you can see in this confusion matrix, we only misclassified one observation. 11 times that we predicted 11, -1, it was actually -1. 8 times we predicted 1, it was actually 1, and only 1 time we mispredicted things. You could just call this anything you wanted. You could just call predict as let's say actual observations. Then your table will show you actual observations here. Okay, so there's nothing important about predict and truth here. But what is important is that we wanted to show our prediction about y versus actual observations of y. Now let's move on to radial kernels and also polynomials. I'm going to explain what radial kernels are. Sorry, how to use radial kernels and how to play with the parameters that are assigned to radial kernels. And as you can remember, we had a gamma term and cost term that were related to such kernels. For polynomials, you can also use the same thing. The only thing that will change is that instead of fixing gamma and cost, you have to fix degree of polynomial. We have this component in it. So I'm going to focus on radial kernels. Using polynomials is easy. You just need to make some adjustments using kernel as polynomial and use degree component. So let's focus on radial components. So in order to do that, let's create some interesting variables. And I explain what we're going to do in a bit. So let's set our seed to 1. And now let's produce a matrix of size 2 to 200. 2 times 200. So 200 observations with 2 columns. So I've created 400 random variables with 2 columns. So I want to do something special here. Let's assume my first category is different from my second category in 2 ways. The first way is the places that has more than, which contains x's that are 2 values more than the first category. And the second category is the values that are 2 values less than 2 categories. For example, let's assume we wanna find medium class people. So medium class people, or better say medium income people, are the ones who are worse than high income people, better than low income people. So here I'm adding 2 to first 100 observations. Okay, so I'm adding 2 to first 100 observations, and I am subtracting 2 from 101st to 150 observations. So these are high income people, these are low income people. So the first 100 people will be the ones that have high income. Second 50 people are the ones who have low income, and the rest will be the medium class. So our goal is just to extract medium level people from or middle class people from non-middle class. And so the first 150 observations belongs to non-middle class, and let's signify that by 1. So the first 150 observations are the ones who are middle class. The second 50 observations, which are the ones that we didn't manipulate, are the ones who were medium class. So let's look at y now. So as you can see, the first 150 observations are medium class, non-medium class, non-middle class, and the last 50 observations were high income people. So among those 100 people, 100 people are high income people, 50 people were low income people. So let's attach all these values to each other, and let's plot it based on the color of y. So y can be 1 or 2 colors. So let's plot it and see how it looks like. So as you can see, we have low income people here, we have middle class in the middle, and high income people at the end. So these are 100 observations here, 50 observations in the middle, and 50 observations here. So as you can see, there is no line that can separate these two values. So we have to use some nonlinear shapes. And as been discussed in earlier lectures, in order to do that, we need to use either radial kernels or polynomials. So here we're just going to focus on polynomials. And just for the sake of this example, let's divide our data into training and test data. So our training will be the 100 observations from the test data we have, from the whole observations that we have. So in order to run a kernel function, we just need to use svm. So that's the name of the function. svm on my y variables, because that was part of my data frame, on x1 and x2. The data we are using is just the part of that DAT data, which is my training. The kernel I'm going to use is radial. Let's fix gamma to 1 and cos to 1 as well. So, and let's plot my SVM feed to this model based on the data I get on training set. So it looks like this. As you can see, it did a pretty good job in separating my lower class people from middle class people from high class and low class people. So we see these couple of guys were misclassified as middle class. This guy is also misclassified as non-middle class, but indeed was middle class. And as you can see, the support vectors look like something like this here. And also there is a support vector here at the end and here. So one thing we need to do is to see what will happen if we change costs, for example. So here we just ran our model based on cost 1. Let's run a new model based on cost 10,000 or 100,000. So let me make it 10,000. Or maybe I stick to 100,000. Okay, so that's the same model just by 100,000 observations. So let's plot it and see how it will look like. As you can see, when we increased our cost, we let it become way more flexible here. So we went after individual observations. So as you can see here, we have small islands here, which is not that cool because as you saw in original data, we had a very significant class at the middle, and it was very easily spreadable. So as you can see, such a cost didn't work, but how can we find the best cost model? Again, the way you use, the way you compare the best model, the way you evaluate different models is through using tune model and cross-validation. So tune does cross-validation for us, and the components of that is very much the same as the components we explained earlier. So you should first introduce what model you're going to use. You're using is SVM. You should introduce what you're regressing on what, and here we are regressing y on everything else. The data we are using is a training data set. The kernel we are going to use is radial, and here you list all the things you want to change. So here we have two parameters to tune. One is cost, the other one is gamma for radial. For polynomials, you would write degree here. So in ranges, you put the list of things you want to change. So in this list, I want to change cost, and the things inside cost I want to check is 0.1, 1, 10, 100, 1,000. I also want to change gamma from 0.5 up to 4. So these are the things we are changing. So let's run this tune function, and let's look at the summary of tune out. It says the best performing model has cost 1 and is gamma 1. Again, if you want to have access to this model, you just write tune out best model. Maybe just for the sake of this example, let's plot tune out best model on our training data and see how it would look like. As you can see, we see these clear distinctions, and it almost clearly, almost exactly divided my data into tuning and onto middle class and non-middle class classes. But one thing we need to do is to look at how it is doing on test data. So let's define test as whatever training is not. And I tried to just minimize writing notation. Maybe I should have just introduced it another way, but I think that's okay. So let's define true as the values of my test data on y. So values of my test data on y are truth. We want to show it in comparison to prediction, and to do it, we need to find prediction method. Our prediction method uses the best model of tune out, and you use test data as new observations. So news is that data on my test data. So if you run this, it will show you a table of true observations versus prediction. So 54 times truth was class 1, we predicted 1. 6 times the truth was class 2, we predicted, okay, in my test data. 23 times it was class 1, we classified it as 2, and 17 times it was class 2, and we classified it as class 1. So our overall error is 17 plus 23 divided by 54 plus 6. Okay, I didn't need the equality here. So my overall, oh, sorry, 54 plus 6. Okay, I made a mistake. Plus 6 plus 17 plus 23. Okay. So my overall error was around 40%. It's significant. It's very high actually. But that's the best error we can get in my test data. So let's review the things we covered by now. The first thing we discussed was linear kernels. Here we need to work on cost. And we showed that if you want to tune it based on cost, you just need to list all the costs you want to work on. Then we focused on radial kernels, and we showed that there are two things to be needed to be tuned. And the way you do it, again, putting all tuning parameters inside a list for ranges. So here we wanted to tune in the cost of gamma. And one cool thing about tune function is that whenever you want to get access to the best model, you just write tune.out $ best model. It gives you the best thing that is out there. SVMs are very powerful nowadays. They're being used all over the place, and that's it. I'm very happy that we covered that part as well. I hope you had fun with it. Thank you. See you next time.